Hello everybody, welcome to the presentation of our study HD versus 4K driven remote tower optical systems. What is the best optical sensor? It was a teamwork of DLR colleagues, Giulia Schön, my person Jörn, Jakobi, Sina, Felten, Giulia, Andreas, Nadobnik, Rambau, and Felix, Timmermann. Some words to my person. As said, my name is Jörn Jakobi, acting as a remote tower expert and business manager in our institute is Institute of Light Guidance, working in the Department of Human Factors. I studied psychology, acting as a human factors expert in DLR since 2000, mainly dealing with airport airside traffic management topics with a particular focus on concept design and validation. And since 2010, I'm almost exclusively working with the development, research and development of our remote tower systems. In this phase, I was responsible for several internal, external, small and huge European, international projects dealing with remote tower development and implementations. And in 2014, the UK group, the standardization group, Working Group 100, Remote and Virtual Tower, has been funded, and I became the chairman of this until today. And in 2019, I received the Manfred Fuchs Innovation Award for my achievements with remote tower innovations and implementations. And last year, I was honored with the UK Working Group Leadership Award. So what is the study about? As the title said, we compared full HD sensors with 4K sensors in the field of remote tower. But what is remote tower? It's probably not known to everybody. It's a very promising concept in air navigation service provision. The first implementation was 10 years ago, and the situation today is we have an airport and a physical remote tower building where the air traffic controllers, the ATCOs, are sitting and monitoring and controlling the traffic. But with remote tower, we're replacing this tower. We get rid of this tower and capture the out of the window view by camera sensors and relay the video streams to a remote tower module where the ATCO is sitting now and operates the traffic. This has several advantages, but with the next step, when we connect several other airports to this remote tower location, which is then called a remote tower center, then we can create additional synergies, so we can better exploit the valuable human resource ATCO, the air traffic controllers. And the next and final step would be that one controller would be responsible for more than one airport, especially for small airports with very less traffic, but then you can exploit the resource much better than before. So this is, in a nutshell, the concept of remote tower, and you see what is a core in remote tower is this optical sensor. Here a picture of air traffic controller in our simulation facility controlling 3 airports at the same time, which, as I said, is called multiple remote tower. So this picture shows the main building blocks of a remote tower system. On the left hand side you have the aerodrome, on the right hand side you have the remote tower center with the human operator, and all starts with the optical sensors who capture the image and bring the video stream to the processing unit, which mainly, among other things, compress the data to provide a good handlebar stream to the network, which is the bottleneck in the system. So it has a certain bandwidth which has to be considered, certain cost. So relaying data is also a costly factor. And on the remote tower center side, on the right hand side, you have the counterpart, the image decoder, which decompress the data and present it to the optical sensor presentation, which usually are huge screens showing panoramas quite similar to the view out of the window. So you can easily see it's not only the sensor size in this class-to-class change, so there are different other possibilities to tune the system. And in the end, it's the performance reflects the best tuning, best orchestrating all the different parameters. So beginning from the sensor size, beginning from the lenses itself. So the field of view can be chosen. The sensors have a different maximum bit rate. Depending on the amount of pixels, you have different bits per pixel. You have a certain amount of bandwidth available for the network. So you have to compress the picture, the streams that it fits to your available bandwidth. You choose the video update rate, of course, that you have the best operational performance in the end. Also, if you present the picture, you have to choose a lot of things. So the picture, the screen size is an important factor. The resolution of the screens, the distance from the operator's eyes to the screens are important, because it's no worse to have a high resolution and then you are too far away from the displays that you cannot get benefit of this good resolution. So all depends on the room where you have the controller sitting, and so a lot of factors which has to be orchestrated in the best way to get the best performance out of it. But what is under focus in this study is we are here on the optical sensor size, and we're comparing different sensor sizes, full HD and 4K. So let's have a look to three main characteristics of HD and 4K cameras. So let's have a look on the sensor first, on the left hand side. So you see the two different sensors, and as you know, 4K by definition has 4 times more pixels. So on the same sensor size, also the pixel size itself shrinks to 1/4 compared to the HD pixel size. So that means that the chance to get the photons on each pixel shrinks as well. So which decreases the light sensitivity. So with new generations, they compensated this effect. They have larger sensor sizes, up to 3/4 of an inch, so that this fact is compensated. But take care, if you deal with 4K sensors, that you have enough sensor size not to shrink the light sensitivity. The second one is bandwidth processing resources. 4 times more pixels needs 4 times more bandwidth needs. So if you have not enough bandwidth and you want to have the same stream amount as before, you have to much more process the 4K streams. So you have new or better or more powerful processing units, which of course needs more energy, power energy, and which would easily heat up your camera. So there are certain limits how many power you can apply for, but they are quite good, these new power units, and rather cheap. So that's why also HD cameras uses this powerful processing units, with the effect which you can see on the right hand side of the picture here. The HD camera has less pixels to relay, but the same power, so the same maximum bit rate. On the right hand side is the HD camera. So there are less artifacts with the 4K camera if you have the same pixel per degree solution. But usually this effect is compensated, of course, with a larger field of view by the 4K camera. And that's why you have a better pixel per degree resolution. Third one refers to high dynamic range. This is also a fact from earlier generations. It deals with a good composition of over and underexposed pictures to get the best detection rate in the air and also on the ground. So very good feature. But this has in earlier generations not been exploited by 4K sensors, but today it's state of the art for both cameras, so not a difference anymore. So having a look on the cameras and the camera specs we used, we mounted 3 cameras on our research prototype camera post. It's very close to our research airport in Braunschweig, and we choose 2 industry cameras that are used in operational installations of today, which are access cameras, here the HD one and the 4K camera. And a third camera has been taken into account. This is our research camera, 5, 6, maybe 7 years old. It's a Sony camera, a CNC VB 770, and we just took this one to compare the newer generation to the older 4K generation. So you can see here HD is abbreviated with HD. We have 4K1 with the industry camera and 4K2 for the DLR research camera. And here you see the specs. So from the lens, sensitivity, light sensitivity, they are quite the same. All are able of HDR. The sensor image size, it's the one I introduced to you. Even the older one has this bigger inches sensor size. The field of view per pixel, which is HD or Ultra HD. And this is the one you can choose. So the field of view has been chosen as they would used today in an operational system. HD cameras usually operate 45 pixels per degree. 4K cameras goes up to 60, 65. Our research type choose for a smaller field of view, which relates in the higher pixel per degree, higher resolution in the end. This is quite normal, 4 times more pixels, all had the same frames per second, 30, and this sums up to the total number of pixels per second. So 30 million compared to 250 million per second. Same video compression, the standard 264 standard. And here you see a difference, the maximum bit rate, maximum megabit per second. As I told before, they developed new powerful compressing features, and the HD cameras adopted this standard, but the older 4K you can see here is still only able to bring 32 megabits per second out of the camera. So this results in a different maximum bit per pixel rate. So HD camera has the same maximum bit rate but less pixels here. So it would sum up to 804 bits per 1000 pixel in average. The 4K only 200 bits per 1000 pixels. And the 4K camera with the lower maximum bitrate only 129 bits per 1000 pixel. Just to keep this in mind. This slide is just to show where we are. You see the runway strip here. It's Braunschweig EDVE airport. The camera were positioned. Here's the operational tower building. And almost here is the camera side, and we had incoming traffic 26 from east, and we also looked for VFR traffic coming from the north, usually flying this pass. So when we look back to the facts I just presented, then we could derive 3 main hypotheses. So thinking about that, the resolution pixel per degree with 4K cameras is slightly better than with HD cameras, but the bit per pixel rate with HD cameras in contrast is slightly better. Maybe these effects counterbalance each other, balance each other. So reflecting this, we set up three main hypotheses. The first one reads, there are no differences between HD and 4 cameras in terms of their detection range performance. So we measured the detection range performance as one performance parameter. The second one is the recognition range performance, all related to Johnson definitions. So detection is seeing there is something. Recognition is in the sense of, oh, I can detect or recognize the object class. And the third performance parameter was some kind of perceived video quality, which cannot, it's hardly to measure in a quantified way. So it was by judgments of the controllers who watched the different video. So as you can imagine, that detection and recognition performance is heavily dependent on the current prevailing visibility conditions. We choose for different environments, different weather or visibility conditions with the run rate 2.6 approaches. So in names it was the CAF OK, which means clouds and visibility OK. With clouds must be higher than 5,000 feet. This is an example picture of it. Blue sky with opposite sun. It's a special challenge for camera detection and recognition performance. Rain, dusk, significant clouds and low visibility. Here you see a picture of significant clouds. Visibility drops in these settings down to 5,000 meter. So on the slide before, you saw the 7 visibility conditions for the run rate 2.6 approaches, which we usually weighted for the Dornier 228 type. So I always use the same type, an IFR approach. Then we turned the cameras to the north to also capture the VFR approaches, and used 3 further visibility conditions. We could not use rain or dusk because it's VFR and they're flying also only in good visibility conditions. So there are small aircrafts like Piper 28, something like that. So you see the approach paths here. They usually fly over November, the mandatory reporting point, November 2. And usually at this point you see the yellow line. This is one example where they were spotted first. So it's a distance of about 6.4 kilometers, which is very far. So about 3.5 nautical miles. Just an example. And to calculate where they were, what is the distance from the camera, we used this red line. The red line is the angle via the church here, which we could see in the video. And with this fixed point, we could calculate by the angle. We could calculate the distance where the aircraft was at this time. Experimental setup. We recorded 6 weeks long with 3 cameras. Once the 2.6 approaches and 3 weeks the north approaches, and 23 ADCOs took part at the experiment, and they were requested to watch the videos. They were, for the run rate 2.6 approaches, we had 3 cameras, 7 visibility conditions, so 3 times 7, 21 videos, and for the north position 3 visibility conditions, 3 cameras, 3 times 3 are 9 videos for the incoming north traffic. And they were requested to watch the videos. They also listened to the ambient airport sound and to the radio communication, so they had a quite good situation awareness. So they knew that the aircraft got landing clearance or first contact to the ATCO. So they watched and clicked the detection button when they first saw a pixel, and clicked on the recognition button when they feel quite confident that they recognized the aircraft class, which is for the runway 26 a medium aircraft size, and for the north incoming traffic it was small aircraft size, like a Piper 28. As you can see here, we used Quad HD screen sized, because we wanted to present the videos in pixel per pixel, so pixel true mode. So we cropped the 4K videos, which has a larger field of view, to have it in the same field of view that they could not distinguish HD or 4K in terms of the field of view pictures. So all videos could be presented on this Quad HD monitor. In a second part of the experiment, the participants, the ATCO, were requested to judge about the perceived video quality. So as said before, we had 30 videos, and the same traffic situation, the same visibility condition were shown with 3 different video streams. They did not know which one was which one, so all had the same size, and they should compare the videos with respect to the experienced motion, so movement, smooth or flickering, where we would expect not a big difference because all operated with 30 frames per second, but then noise, in terms of noise or noise free, the color quality in terms of colors bleeding versus very natural, and the edges at the pictures blurring or sharp, and textures like moving trees in terms of blurring or also sharp. And they had sliders, so they could bring, because there's not definitive end or beginning point of this perceived video quality, they brought the judgments into relation to the videos, so they could simply judge which is the best one, which is second, and which is third place, and also the distances of the quality. So coming to the results, starting with the detection range performance results. So what you can see here is a runway 26 detection range performance bar chart statistics for distances, nautical miles, via the independent variables, weather, visibility, and the camera. So you have for each visibility conditions 3 cameras. The overall main effect, as you can see, due to the cameras, distances is not significant. You can see here there. But as expected, of course, there's a significant weather effect. This was expected, but as the hypothesis says, detection of differences between the cameras are not to be expected, on the main effect at least. If you look to the single visibility condition, there are differences, not in blue sky and K4K conditions, but the 4K camera performed better, performed better in clouds, low vis, rain and sun. But in dusk, in contrast, the HD camera was much better than the industrial 4K1 camera. This is due to the fact that the 4K1, the industrial cameras, was tuned very underexposed, so it performed very well in direct sun conditions, as you can see here, but in contrast performed worse than in dusk conditions. So dusk conditions are quite good, or almost similar in the performance range of the sunny conditions, because you can see the approaching light quite well. So that's why detection performance is quite good in dusk. Next slide, again detection range performance, but with small aircraft coming from the north. Sometimes they were not detected at all, so there was just small pixels, and if you by accident watched at the right spot, then you could see it. Sometimes controller simply missed it, which also would happen in traditional tower out of the view. As you can see here, the distances in nautical miles, so small aircraft usually was detected in 2 to 3 nautical miles, which is quite a reasonable performance in terms of range. And in this pie chart you can see if it's detected, then it's gray; if not detected, then it's white. And you can see that the cameras do not really differ. So HD, for instance, is better than the 4K one. In K4K, sun yes, clouds no. But here it's worse than the 4K, but in general it's slightly better than the industrial 4K. But this is heavily depending on the camera settings itself. So no big differences, as you can see, in accordance to our hypothesis. Regarding recognition, a similar pattern to what we had with detection already, just that the aircraft has to come closer. You need more pixels to judge about the object class. So there is, of course, a visibility weather main effect, of course, but also a camera effect here with recognition. But as the camera weather interaction also became significant, the other main effects are hard to interpret. That's why you have to look into the single comparisons again, where we found significances in a similar pattern with detection. So the 4K camera with the underexposed setting was worse in dusk compared to the other 4K, and the HD camera is this here, but significantly better in low vis, rain, and sunny conditions. So next is perceived video quality, which relates to our third hypothesis. So the first two hypotheses could be proven. There are no significant differences in detection and recognition, and third hypothesis postulated that also with perceived video quality there would be no differences, but there were differences. So the first test was each single video presentation had to be judged quite generally. Please judge about the quality of the video. Quite hard task because you do not have a comparison, but as the ADCOs did not know which video camera they saw, it's quite reliable results. So, and in general, the 4K one camera has been significantly proven better than the 4K2 and much better than the HD cameras. So you can see in this box plot here diagram. Second test was to judge about the readability of a lettering sign, which is hardly be seen in this slide here, but here there's a lettering sign with the letters DLR, and they should judge how well they can be written, can be read. And also here, same pattern, significantly differences with 4K2 to HD. The 4K cameras did not differ, not significantly, and again HD and 4K1 much better, as you can also see here in the box plot diagram. So on average they judged 4, the 4K2 camera an average 3, and the HD camera just 2, with ratings from 1 till 5. As said, in part 2 of the experiment, the test subjects were asked to judge the perceived video quality in between of the 3 simultaneous presented camera video streams via all 10 different weather visibility conditions. Their answers were summed up over the weather conditions and the camera cam condition compared against each other via the 5 different video quality categories: motion, noise, color, textures, and edges. The results are presented descriptively via median box plots and proven by interferential statistical analysis pairwise t-tests, except of the motion category, where we did not expect any differences because all cameras worked with 30 frames per second. All other categories, the 4K one, the industrial camera, was always significantly better than the HD camera. Conclusions. So the overall goal of the study was to compare the performance of 4K and Full HD cameras in an RTOS environment, focusing on detection and recognition range performance and on subjectively perceived video quality. And the answer is, there is no clear answer. As said in the beginning, there are so many factors contributing to a desired performance that makes a decision just on one parameter rather difficult. So in fact, we have to say, regarding the main effect camera, at least in this setting, there are no significant differences between HD and 4K cameras in terms of their detection and recognition range performance. Again, there are significant differences in between of the cameras and under different weather conditions, saying quite often the 4K shows the better performance, but also the HD has its advantages, for instance in dusk conditions. Regarding the perceived video quality, there were significant differences. Contrary to the third hypothesis, the 4K cameras are perceived to be sharper in terms of textures and edges, with more color fidelity and lower noise. This result is supported by 2 further tests in which the test subjects were asked to generally assess the quality of the video and also to assess the readability of a lettering sign 240 meters away. In both tests, the 4K cameras performed significantly better than the HD camera. The 5th bullet reads, in a 360 degrees composition of several individual cameras, it is to be expected that the slight advantages of the 4K technology would become even more apparent. But what does this mean? Let's look again on the camera specs. So let's have a look here. Main effect of 4K cameras is, of course, we have 4 times more pixels than with Full HD cameras. So we can even afford a bigger field of view and still have a better angular resolution. So in this setting, it's 45 pixels per degree for the HD and 65 pixels for the 4K, where you would say detection and recognition range should be better. But as said, more pixels, same frame rate, needs more demand on delivering the pixels. So we have 250 million pixels instead of 62 million pixels, and there is a limitation in terms of bitrate. So the maximum bitrate for both cameras is 50 megabits per second. So to bring this in relation means that the HD can deliver or can perform 800 bits per 1000 pixels, the 4K only 200 bits for 1000 pixels. So there are 2 effects, this ratio here and the angular resolution here, so which probably balancing these effects in terms of the performance in the end, what we actually measured. But next fact is that in an RTOS we do not have a single camera. So typically we deliver a 360 panoramic video stream with multiple cameras arranged in a circle, which sums up the horizontal field of view of each camera into an overall 360 panorama. So in our setting with a 4K horizontal field of view of 60, you can see here, we would need 6 cameras. Better 7 because we need some overlap when the streams get stitched to each other. So with the HD cameras with a horizontal field of view of 43 degrees, at least 9 cameras would be needed for a full 360 degrees panorama. 2 more than with the 4K panorama. Have this in mind. With a maximum data stream of 50 Mbit per second for each camera, the 9 HD cameras would consume 450 megabit per second. The 4K panorama, just 7 times 50, equals 350 megabit per second. So the bandwidth needs for the HD panorama would be much higher, and so the costs. However, both 450 and also 350 megabit per second would be much too much and too expensive for most prevailing infrastructures. So the data streams have to be further compressed down to typically used maximum of 100 megabit per second, sometimes even lower, depending on the prevailing infrastructure and other constraints. So to achieve this, the HD panorama stream has to be compressed much more than the 4K panorama stream. In numbers, factor 4.5 compared to 3.5 to achieve these 100 megabit per second. So it cannot be stated directly what would come out of this with this setting, because this panorama setting has not been tested. But one would assume that the performance of the HD will continue to lose out compared to the 4K panorama solution. Yeah, and another side effect in this example, look to the field of view again. The vertical field of view of the 4K would be higher, so 33 degrees instead of 24 degrees of the HD panorama. That's why you usually in an environmental setting you use the cameras in portrait mode, but with the fact that you even need more HD cameras, which again consumes more bandwidth, and you have to compress much more. So back to our conclusions and outlook slide. The last bullet reflects an outlook. As just seen, all cameras use the same codecs in this setting. It's H.264 codecs. Yeah, but as you know, there are more modern codexes like H.265 or AV1, which allow a higher maximum bitrate, which possibly could improve the overall quality of the video stream. But you have to consider that the encoding principle of modern codecs tend to eliminate small details, which could even lead to a reduction of the detection performance compared to H.264. So this could be worth a future study to compare the end-to-end performance of different state-of-the-art codexes. So very last slide is just stating that is the end. There are most probably much more specific details with respect to the results and the experimental setting in the study, which I could not refer to in the amount of time we had here. So if you have further questions, do not hesitate to contact me. Here's my email address, and let's get in touch. Goodbye.